Hello everyone, thank you for your time for 26th International Conference on Mechatronic Technology, ICMT 2023. For today's presentations, our paper is about cruise control development and hardware in the loop validation for electric motorcycles. The author of this paper is firstly me, Muhammad Akimullah bin Subari. Secondly is Thuong Min Ngọc Bui. Thirdly is Thuong Quang Dinh, and the last one is Jong Yun. Okay, firstly we will start our presentation with an introduction. Okay, as we know that electric motorcycles, EMS, is plug-in electric vehicles with a two-wheel. So this electric motorcycle, the power is supplied by a rechargeable battery that drives one or more electric motors, as compared to the conventional motor in the market now, which is powered by gasoline engines. And basically this electric motor has several advantages, which is it is less maintenance. Secondly, it is environmentally sustainable. And the third one is it is easier to operate. And the last one, it is extremely fast and powerful motorcycles. Okay, next we will go to the VSC, which is Vehicle System Controller. So VSC, it serves as a central control unit which is responsible for managing and coordinating various vehicle systems to ensure the safety and to ensure the efficient and smooth operation of electric vehicles, or in our context is electric motorcycles. Next, VSC has several functions and responsibility, such as it will integrate all the vehicle systems. It will ensure the safety and stability controls of the vehicles, such as rollover control or traction controls. And then in VSC also we can have drive mode selections, which normally we know we have 4 driving mode selection, which are rain mode, eco modes, sports mode, and normal modes. Next, in the function of VSC also we can have ADAS systems, which is advanced driver assistance systems. And next we can also have an electric and hybrid vehicle system inside the VSC, such as battery management systems. And lastly, in VSC it also has a capability to diagnostics and found what error or problems we have on our electric motorcycles. Okay, one of the VSC systems is cruise controls, or normally known as CC in the short forms. Okay, CC was developed to hold the throttle in a fixed position and allow the vehicles to travel at a constant target speed. Okay, there are 3 main advantages of CC, which is first, it will reduce the mental and physical fatigue of the driver. And the second advantage is it will maintaining the fuel efficiency, because you doesn't need to like sudden pressing the throttle position or sudden pressing the brake. And the third one is it will improve your comforts during driving. Okay, next, in order to develop the cruise control systems, there are 4 main things that you need to have. First, you need to have the actual bike speeds. The second one is you need to know what kind of driving modes you are now. As I mentioned earlier, we have 4 driving modes. The third one is you need to have the throttle positions, and the lastly is the speed limit. Now we will go to the HIL, which is hardware in the loop. HIL is a technique that is used in the development and testing of a complex real-time embedded systems. So for the application of HILs, normally it can be found in system control developments and verifications. Besides that, HIL also applies during product developments and assessments and for the system performance validations. So basically, when we are applying hills in our development systems or our verifications, there is two main benefits. The first benefit is it will reduce the time spent for testings, and the second one is it will reduce your overall cost required. Okay, we go to the cruise control strategy development. As we can see in the slides on the left figure, it shows the flowcharts of cruise control strategy proposed in the study. As we can see, it has three different modes, which is off mode, enable mode, and active mode. To go from one mode to another mode, there is certain conditions that must be met. For examples, from off mode to enable modes, the condition is the cruise control buttons must be pressed more than 0.5 seconds, and the vehicles must be in drive states, which is here is in number 5. Then from enables to the active modes, the CC button must be pressed between 0 to 0.5 seconds. The bike speed must be more than 20 km per hour, and the vehicle must be in drive states. Okay, similarly, if you want to go from active mode to enable modes, the button must be pressed between 0 to 0.5 seconds, or if we press the brake, we will go from active to enables, or we press the kill switch buttons, or we push the side stands down. Besides that, we can also go from active mode to the off modes, which is we must press the CC buttons more than 0.5 seconds. Okay, if you want to go from enables to off modes, similarly, the CC button also must be pressed more than 0.5 seconds. Okay, and for the on the right figure, you can see that the cruise control strategy that we developed in the MATLAB Simulink by using a state flow method. Okay, after developing the cruise control strategy, we need to develop the control design for our cruise control. So as we know, there is a lot of type of controller that we can use, such as PID controller, SMC controller, or advanced controller. But in this study, we will propose a classical controller, which is PI controller, where P is proportional and I is the integrational. So the input of our controller is the error between the cruise reference speeds minus actual bike speeds. That is our input of the controller. And the output of the controller will be the throttle positions, which will fed into the plant's model. Okay, as I mentioned early in the slides before, we have a plant models. So here is our plant models, which is 1D model of electric motorcycles. As you can see that in the dash red line box, we have 7 subsystems of plant model, which is we have battery model, we have BMS, battery measurement systems, we have motor model, we have inverter models, and we have also chassis model, which is we have the dynamic model of the vehicles, the wheel and brakes of the vehicle, and the transmissions of the vehicles. So the output of the battery is the battery current request, which will go to the BMS, battery management systems, which will provide the output of I, battery current request, and torque request, which will fed into the inverter. And the output of inverter is motor current request and torque request, which will go to the motor before being fed to the transmission and the wheels. Now we will go to the hardware in the loop implementations. As you can see in the figure, this is our hill configurations. On the left side is the what the hill platforms that we developed in our lab, where we have a host desktops, we have the micro auto box, we have the Scalexio, we have the telematics, we have the ECU, and we have the CAN logger. So in our host desktop PC, the software that we use is the DSpace and MATLAB. And then in our micro auto box or MAB, we have inverter models, we have motor models, we have battery and BMS models. In the Scalexio, we have rider simulator, load simulator. We also do have our transmissions, wheels, and dynamic models. In telematic, we have telematic device. So basically, this telematic device will transfer the output data to our own clouds. And in ECU, electric control units, we have our torque management. We do also have our cruise controls, where we developed in this study is in the ECU. This is our hill platforms that we developed in our labs. So as I mentioned earlier, we do have the Scalexio. As you can see on the right figure, we do have a breakout box for the connections between input outputs between the Scalexio or between the micro auto box. So we do have our ECU compartments, and we do have the PSU, which is power supply units. This PSU is needed to power up the micro auto box and to power up our breakout box and ECU. Okay, now we go to the results and discussions. As I mentioned earlier, we use a PI controller for our CC controls, which is to ensure that the vehicles can accurately track the desired speeds. The parameter of PI controller is KP, we set it at 50, and KI, we set it at 0.1. Okay, to validate our CC in hills, two reference speeds were chosen, which is 30 miles per hour and 60 miles per hour. So the reasons why we choose these two speeds, because it represents the UK national speed limit for suburbs area and single carriageway. Okay, as you can see from the both figure, the red line represents the vehicle speeds. The blue line represents the vehicle torque demands, where negative torque is a driving torque and positive torque is a regen torque. And lastly, the grid line is the throttle positions. Okay. It is noted that the throttle position is automatically controlled during the CC operations. So the rider is only controlling the directions and managing the stability of vehicles during these hill validations. Okay, as we can see that for the cruise control performance at 30 miles per hour, at point 1, 24% of total input was given, which resulted the vehicle to generate a torque of around 10.25 Newton meter. Then at point 2, we enable the CC by pressing the cruise buttons more than 0.5 seconds, as I mentioned in the flowcharts of the CC's control strategy development. Okay, when the vehicle reached 30 miles per hour at point 3, the CC button is pressed once more again to indicate now that we are in active mode, which is CC is active. Okay, and at point 4, we release the throttle positions, which is allowing the regenerative decelerations to slow down the bike. Here, the bike speeds will be reduced until it reaches the cruise reference speeds, and at point 4, the CC is returned to enable modes, reducing the bike speeds. Okay, similarly, with the cruise control performance at 60 miles per hour, we enable the CC at 0.1. Then at 0.2, which is around 60 miles per hour, we set the CC to active, and the throttle is released at 0.3 to observe the CC performance. Okay, and the green table show the percentage of difference between the cruise reference speeds and the actual vehicle speeds, so that, and we can see that at 30 miles per hour, around 1.49% percentage of difference, and at 60 miles per hour, around 6.51 percentage of difference were recorded, which is acceptable for both cases. Okay, we go to the conclusions. I think the last part, which is conclusion. This study presents that the development of hill validation of the CC systems for an electric motorcycle applications, and we can see that the results show the proposed CC systems and hill validation procedure recorded less than 70% speed tracking error for both cases, which is 30 miles per hour and 60 miles per hour. And for the future works, maybe we can do a PI controller parameter optimizations, which we haven't done in this study. So different method or different tool can be used, such as PSO, particle swarm optimizations, or GSA, gravitational search algorithm, to optimize our controller parameter. Besides that, for future work, we can also implementations. Yeah, we also can implement an advanced controller, which we might use MPC or sliding mode controller, where this type of controller are more robust. And then we also can use implements and adaptive cruise control for the future work. I think that's all from me. Thank you very much for your listenings, and this work was supported by Innovate UK through Electric EBSA, which is project number 75281, with the collaborations between WMG, which is ours, BSA, Hypermotive, Dana TM4, Microlize, and Vital Auto. So if you have any questions, please do not hesitate to email me. And once again, thank you very much for your times. Bye bye.